Okay, so this is the real deal now. So we're going to learn ARM's architecture. So the first tell you more about the assembly language, machine language programming, addressing mode. I mean, that's the whole chapter 6. So we'll start from low level and simple instruction. We build up with the format. At the end of the chapter 6, if I give you 8-bit hexadecimal number, you need to give me one instruction. Into high-level instructions, CMP, BNE, add, subtract. Or if I give you add R0, R1, R2, you should be able to give me 32-bit binary numbers and 8-bit hexadecimal numbers. That's what we're going to learn from this chapter. So basically, high-level, program language to very low, we call machine language, zeros and ones. So assembly language is the human readable format instruction, and the machine language is the zeros and ones. So we're going to learn how we go from here to here, and we'll look at the architecture. And then chapter 7 is the microarchitecture. So meaning how we're going to make the computer process this X number of instructions through single cycle data path, multi-cycle data path, and pipelining data path. ARM architecture developed in the 80s, nearly 10 billion processors sold every year. Almost all cell phones, tablets, the ARM everywhere. And if you learn one architecture, it's much easier to learn any other architecture as well. So our book is basically based on Hennessy and Patterson book that we used to use. So in the Patterson and Hennessy, designing the architecture of any machine, we should follow these 4 kind of rules. Regularity supports the design simplicity. That's why we are using only 32 bits. Make the common case fast. Smaller is a faster. Good design demands a good compromises. So you are given A equals to B plus C, A equals to B minus C as a C code. In the ARM's architecture code, it's going to be add A comma B comma C sub A comma B comma C. So the first 3 letters, all capital, that's what operation to perform. Add, subtract, CMD, MOV, so capital 3 letters. We're gonna look at bazillion instructions in the ARM, so many. We're gonna have 3 components, but sometimes 2. A comma B is possible, and I'll show you later with the numbers and all mixed up. However, first letter right after this mnemonic is our destination register. First letter always is going to be our destination. We need to do add. What do we need to add? What? Content of register B plus content of register C, and the result, put it into A. Content of register B minus content of register C. Actually, content of register B plus 2's complement of content of register C, add, put it in here. So A is our destination. So the first design principle is this. Now, if we have 3, A equals to B plus C minus D, now you will be given later which register you're going to use, but let's use just B and C and D. We can have temporary register T, and then we have to do 2 at a time. There is no instruction. We can do all these 3 at a one shot. So we need to add B plus C first, put it into temporary register T, and then T minus D, subtract. Then put it back to A. That's how we do it. So design principle 2, we can talk about RISC architecture and CISC architecture. CISC architecture is they have a variable length of registers, so it's really complicated. But ARM architecture is a RISC architecture. So we have everything, all the instructions, they have to fit into 32 bits. So it's much easier to decode because we know exact number of bits for instructions, and we know based on the format, first 4-bit is the condition. We'll talk more about it, but that's how we do it. So operand location, physical location in a computer, registers, constant, and memory. So ARM has 16 registers, okay, only 16. And registers are faster than the memory. In the memory hierarchy, we have register right next to me. I'm the processor. And then we have a cache, and the main memory is far away. So if I can use cache or register right next to me, it's much faster. I mean, we're talking about 10 to the power of -9 or picosecond, something like that. But it adds up. And each register is a 32-bit. So ARM is called the 32-bit architecture for our class. And then the third principle, smaller is the faster. So that's why we have a small number of registers. So registers, we go from R0 to R15. We wrote A, B, and C here. That's the first and last time we're going to do it. Now we're going to actually use R0 to R15. R14 is a link register. R15 is a PC program counter. R13 is the stack pointer. It's a reserved. And you don't have to worry about knowing which one is a which. But for our example, I'm going to freely use anything R0 to any. When you have a R0, we're going to say register 0 and save the register R4 to R11. I mean, those are something that you can take a look at it. So now we have A equals to A plus 4, B equals to A minus 12. I can give you this C code and I'll ask you to change it to ARM's instructions. And you'll be also given use R0 as a register A, R1 as a B. This will be given as well. Then now you need to write something like this. So in the previous example, we have all three operands as registers, but this time we have two registers operands, and then the third one is the constant. So we can do that. So again, the first register is our destination register. So R0, A equals to A plus 4, and then subtract A minus 12 and put it into R1, which is B. You see the sharp? That's the decimal number. If you don't see any indication of the number, so we're going to use both decimal number and also hexadecimal number here. So you have to distinguish this. Hey, this is the decimal. Hey, this is the hexadecimal. So your answer is going to be completely different. We have a move instruction. I want to put A as a 23 as a decimal number. Then we're going to use move R0. That's our destination again. And then whatever the constant, dump it into move. So in the move instruction, MOV, we don't need three operands, only two operands. First one is a register. We want to put that in, and then any numbers, either decimal or hexadecimal or even binary. And constant must have less than 8 bits of precision. And also move can also use two registers. So what do you mean by 8 bit? So this guy, we can take only 8 bits, meaning only 2 bits of hexadecimal. Why? We'll see that later, but based on the format of the move instructions. Now, the memory. So we're going to look at the two memory related instructions, and sometimes too much data to fit it into 16 registers. We want to move that into main memory, or we want to read it from main memory. So those are the two. We want to store into main memory, or you want to take it from main memory. Each data byte has the unique address, and then 32-bit words, 4 bytes. So word address is increment by 4, meaning this is memory for our ARM. How many bits for width? What's that? 32 bits. Thank you. If it's a 32 bits, how many bytes? 4. So this is byte 0. If I use capital letter B, it's a byte. Lowercase b, it's a bit. So this is byte 0. This is byte 1. This is byte 2. This is byte 3. And then byte 4, it's going to place in here, right? 5, 6, byte 7, byte 8. So those are the actual name of the byte in the main memory.
Hey, Dr. Kim, I don't want to do that way because I want to write byte 0 first.
Okay.
Can you do this?
Yeah, sure. But we have to be consistent, right? So if you start from the left, always start the left to the right. If you start from the right to the left, always. Now, if we look at this guy first, byte 0, 1, 2, 3. Big number at the end, right? So we call this is big endian. This is small number at the end, little endian. So those are the two different architecture. One is a big endian, another one is a little endian. So this is the little endian. Byte number 0 is right there. So this is the little endian. And then if you write this, it's a big endian. Yes, it depends on the architecture. They use differently. So in the MIPS architecture, is always it was a big endian. For the ARM architecture, we can take either way. Okay, so there's so many variations. For our class, I'm gonna stick to big endian. If this is the big endian, we need to indicate the memory address, right? So memory address in here, I'm gonna just pick the first one, 0, 4, 8, 12, 16, and on in the decimal number. That's why we said 32-bit word, 4 bytes. Therefore, the memory address going up by 4, increment of 4.
Hey, Dr. Kim, what about little endian?
Same thing, we can use memory address as 04. So that's little endian case. So this is the big endian one. So word, put it up here. Byte 0 goes first and then the rest. So first, reading memory. So it's a reading memory. We're gonna use LDR. And format is R0, comma, bracket, R1, and number. So what do we do for LDR? We're gonna read from the memory. The first register is what? Our destination register. We're gonna go into memory and take the content of that memory, put it into R0. Make sense? So our destination is R0. Now, where to go? In the main memory, there's addresses, right? So we need to go exact location 16 or 0xFFFF. We need to go very specific location and then read the 32-bit, bring it to R0. That's what we want to do. How we calculate the exact location of the memory? Content of R1 plus whatever this number. That will give us exact location of the memory. This is our destination, first one. And then content of R1 plus this constant, content of R1 plus constant equals the memory address. Now, LDR is loading from the memory to register, right? STR is store into memory. It's completely opposite. And its format, register some number. I'm sorry, I lied to you. This one is not the destination. This is the only exception. STR is the only exception. The first register is the source register. So what do we do? We'll come back to this. Just listen, try to understand, and then we'll come back to this next time. STR, store. What do you want to store? Content of register, R9. Again, we need to calculate exact location of the memory, right? So now, where content of R1 plus hexadecimal number 14, add those two, that'll give us exact location of memory. So put this into that location. So this guy, actually, after we execute this instruction, we change the content of main memory, right? Okay, so we'll come back to that.